Hello, I'm here to help you solve the following problem. The problem reads, find the equation of the normal plane and osculating plane of r of t is equal to cosine t, comma sine t, comma ln cosine t at point 1, 0, 0. So, to find the normal plane and the osculating plane, we need two things. We need the unit tangent vector and we need the binomial vector. Both of which we can acquire with what we have given. So the unit tangent vector is equivalent to r prime of t divided by the magnitude of r prime of t. So let's solve for that. R prime of t. Okay, so the cosine of the derivative of cosine is negative sine. Derivative of sine is cosine. And the derivative of ln of cosine of t, we're going to use chain rule for that. We're going to have 1 over cosine of t times the derivative of cosine of t, which is negative sine. So this is basically negative sine divided by cosine. And we can rewrite that to say this is equal to negative tangent of t. Here's our r prime of t. So next thing we need is the magnitude of r prime of t. Okay, so to find this magnitude, we're gonna have to square root all this squared. So negative sine squared is just positive cosine, positive sine squared, plus cosine squared, minus plus, because negative tangent squared is positive tangent squared. So here's the magnitude. Through a trigonomic identity, we know that sine squared plus cosine squared is equal to 1. So we can rewrite this to say 1 plus tangent squared of t, which through another trigonomic identity, we know that 1 plus tangent squared is equal to secant squared t, which the square root of secant squared would just be secant. So that is our magnitude of r prime. So now let's divide. So the tangent of t, the unit tangent vector of t is negative sine t cosine of t and negative tangent of t all over secant. However, we know secant to be equal to 1 over cosine. So we can rewrite this to be even nicer looking. So negative sine divided by 1 over cosine would just be negative sine cosine. Cosine divided by 1 over cosine, just cosine squared. And we call it, this is a negative sine over cosine. So if we divide that by 1 over cosine, the cosines will cancel out, which will just leave us with a negative sine. Ooh, pardon me, that looks rather disturbing. Okay, so this is our unit tangent vector, and let's solve for the normal plane before we go into the osculating plane. So we're gonna take this at 0. Any point would work, but this is much easier at 0. So we're gonna have the unit tangent at 0. It is equal to all these values at 0. Okay, so sine of 0 is 0, so this will just be 0. Cosine at 0, that's 1. And sine at 0, that's 0. So this would be our unit tangent vector at 0. Okay, and to find the equation of a plane, we will multiply this, or not multiply, we will use a dot product, r minus r naught. Okay, so our r naught is this point right here, so we can rewrite this 0, 1, 0, dot x minus 1, or yeah, x minus 1, y minus 0, z minus 0, and now we just do the dot. So this would be 0, x minus 1, plus 1, y minus 0, plus 0, z minus 0. So this is all just equal. Y is equivalent to 0. This will be the equation of the normal plane. This. So that is the equation of the normal plane. So to find the equation of the osculating plane, let's work on the back where we have more space. Allow me to rewrite the unit tangent vector here. So that was negative sine t cosine t. Cosine squared t and negative sine t. So let's find the normal vector from this. So first we have to find the derivative of the tangent vector, or the unit tangent vector. So let's find that. So here we're gonna utilize product rule. So we're gonna keep the first the same, and we're gonna divide the second, which should also be negative sine, plus derivative of the second, which would be negative cosine, times cosine. So this will end up becoming negative cosine squared t times sine squared of t. So that is our first one. That's the first one. Now deriving cosine squared of t, this will be, through chain rule, it'll be 2 cosine of t times negative sine of t. And now deriving a negative sine t, that'll just be negative cosine of t. So here is our unit tangent vector first derivative. But we can reduce this to make it look way better than it does now. So to use some trigonometric identities, we know that cosine squared of t times sine squared of t, that is equal to negative cosine of 2t. That is a trigonometric identity. These two are equivalent to each other. So same goes over here. This will be through a trigonometric identity. This is equivalent to negative sine 2t And we can just keep that negative cosine of t. So this will be a much easier unit vector to find the magnitude of. So now let us do that. So here we have cosine squared of t, 2t, plus sine squared of 2t, plus cosine squared of 2t. Okay, so once again, through the trigonometric identity we used before, cosine squared plus sine squared, that is equal to 1. The inside, it is equal to 1 for any value inside. So regardless of the fact that this was 2t, it is still equal to 1. So this would be 1 plus cosine squared of t, which I don't believe can be reduced. So this is our magnitude unit vector of the first derivative of tangent t. So now, let's find the n of t, the normal vector of t, which is equal to the first derivative divided by the magnitude of the tangent vector. So let us do that. Negative sine 2t and negative cosine of t. All divided by square root of 1 plus cosine squared of t. Okay. Now, so now we have the normal vector of t. So we want to find the binormal vector of t, which is the unit vector, the tangent unit vector times the normal unit vector. But since we are trying to solve for the equation of the plane, we are gonna take this normal vector at point 0, because we had already taken the unit tangent vector of t at point 0. So I'll plug 0 into everything. So negative cosine of 0 would be a negative 1. And down here, cosine of 0 would be 1. 1 plus 1 is square root of 2. So this would be the negative 1 over square root of 2. Okay. Negative sine at 0 is 0. So regardless of what happens, that'll be 0. Negative cosine of 0, that's just negative 1. This remains square root of 2. So we have, once again, negative 1 over square root of 2. So this is our normal vector at point 0. So now we can take the tangent vector at point 0, and we can cross multiply them to find the binormal vector at 0. So now, if you don't recall, the unit tangent vector at 0 is equal to 0, 1, 0. So now we're going to cross it by this. Negative 1 over square root of 2, 0, negative 1 over square root of 2. So let's cross it. So 1 times negative 1 over square root of 2 is just that. And 0 times 0 is 0, so it'll just be negative 1 over square root of 2 minus j. So you know j, so that'll just be 0 times that, 0 times that, that'll be 0 plus k. 0 times 0, 0 minus 1 times a negative 1 over square root of 2, that'll be positive 1 over square root of 2. And now this would, and now we have our binormal at 0, which is negative 1 over square root of 2 plus, or I should say, I negative 1 over square root of 2 plus k over 1 over 2. And now we can do what we did on the previous side of the board. We can multiply this by, to find the equation of the plane of r minus r naught, set it all equal to 0. Oh, not multiply, my bad. We can take the dot product of this. Okay. So we're gonna end up with 1 square root of 2 of x minus 1 plus 0 of y minus 0, which will just be 0, plus 1 over square root of 2 z minus 0 is equal to 0. So this will end up being, actually let's make some room here. I'm sure we can erase this. Some room here. This would be negative 1 over square root of 2x minus, or plus 1 over square root of 2 plus 0 plus 1 over square root 2 z is equal to 0. And now we can just factor that out. So this is all divisible by 1 over square root of 2. So let's divide it. Eliminate it. We have negative x plus 1 plus z is equal to 0. And this is your equation for the osculating plane. So here we have the equation for the osculating plane. And here we have the equation for the normal plane. And this, ladies and gentlemen, is how you solve this problem. Thank you.